Hi, my name is Scott Simpson, and today we'll be talking about rate laws. So rate laws determine how quickly a reaction occurs. Now, oftentimes the generic rate law is written along something like this, where we have our rate is equal to some constant times the concentration of a certain species raised to the power of x times the concentration of another species times y, or raised to the power of y. Now this is known as a bimolecular reaction, and what I mean by that is we have two molecules reacting in order to form a product, which we are measuring the rate constant of, or the rate product of. So, when we look at these, if we were to say, oh, let's have a unimolecular reaction, all we'd be concerned about is A, and we wouldn't include B. If we were to do a trimolecular system, we would have three reactants, A, B, and C. All right, so oftentimes in general chemistry, what they do is they give you a table that looks something along the lines of this, where you have the rate, which is in molarity per second. And they're going to monitor the rate as a function of the concentration of A, which is usually a molarity, and the concentration of B. And now I'm going to come up with some fictitious numbers to make the math a little bit easier, so hopefully we can understand more about the chemistry that's occurring and not so much about the mathematics. We will have to go into detail on some of the mathematics in a moment, though. All right, so we have to find the exponents. So remember, we have a generic rate law. Rate is equal to some constant, which we'll determine in a minute, times A raised to the power of x, that's the order, that x value, and B raised to the power of y. So we're trying to find the order with respect to A in this case. So what we have to do is follow a generic equation. Be sure to write this down. I'll refer to it later. So how do we find that order? Well, the way I like to do it is, so you have the rate at some time 2, or the rate at 2, over the rate of 1 is equal to the concentration of whatever species you're looking at. We're going to be looking at A at 2, divided by the concentration of A at 1, all raised to the power of x. So, what do we do from here? Well, we plug in values from that previous table that we looked at. So, if we have rate 1 or rate 2, we have to find a point in time where our concentration of A is changing, but our concentration of B is remaining constant. If you looked at the first two entries of that table, where the rate was equal to 1 and the rate was equal to 2, that would be a case where A is changing, but B is remaining constant. So, let's plug in our values. So we have 2 over 1 is equal to also 2 over 1 to the x. And if you're pretty good at math, you can see that x should be equal to 1. But let's go through an algebraic explanation on how this occurs. You actually have to use logs to figure this out. So a generic rule of logs is if we have, let's say, y to the power of x, that is also equal to x times the log of y. So in the case of what we've done here, if I go through the algebraic manipulation, what we've actually done is taken the log of 1/2, or 2 over 1, which is equal to the log of 2 over 1 times x. when we manipulate this around, we end up getting log 2 over 1 over log 2 over 1 is equal to x, and that's just equal to 1. So that's the algebraic manipulation I did to get to that point. All right, so it looks like our exponent here for a, or our order, is going to be 1. All right, let's find out what it'll be for b. What is the order with respect to b? So we have to follow our same equation again. Rate 2 over rate 1 is equal to b, concentration of b at 2, divided by concentration of b at 1, all raised to the power of y. All right, so if you look at our table again, we'll have to look at the first entry and the third entry. Why? Because a is remaining constant and b is changing. So that's how we can get the order. So we have 4 over 1 is equal to, I guess I can just do it this way. It's equal to 2 over 1 to the power of y. All right, so let's use the logs to figure this one out. You can obviously see that y is going to be equal to 2, but if we want to be very precise and thorough in our mathematics, we should show this. So the log of 4 is equal to y times the log of 2. Log of 4 divided by log of 2 is equal to y, which is then equal to 2, like we have previously shown. So our rate looks something along the lines of this. Now, we have to figure out the overall order. So what you do for the overall order is you add up the orders of each individual component. So, overall order. In this case, what we end up doing is we just add our x and our y. So I'm going to go O order is equal to x plus y plus dot 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 dot. So that's if you have something larger than a bimolecular reaction. If you go up to a trimolecular reaction, you'll have to add up all the orders. So in this case, it's just 1 plus 2. So our overall order is 3. All right. Next, what about the rate constant? How do we figure out the units of the rate constant? So, units of rate constant. Which is that little k. So, let's take our generic reaction again. Rate is equal to k. Well, we'll just go with the one we actually have. A to the power of 1, B to the power of 2. Now, our rate must be in molarity per second, assuming the concentration of our species is given to us in a molarity per second, or a molarity. So each of these guys is going to be a molarity for their units. And notice that they're raised to coefficients. What we have to do is figure out what is going to be the units of the rate constant by manipulating this equation around. So, this will also show us how, if we wanted to solve for k, how we would do that. So, rate is equal to a to the power of 1, b to the power of 2. Now, if we want to find the units, all we have to do is just sub whatever units we're looking for in. So, for example, for our rate, we would sub in the units of molarity per second. Then, for the units of our concentrations, we just have to toss those in, m to the power of 1, m to the power of 2. When we manipulate that around further, what we end up with is molarity over seconds times molarity cubed. We'll cancel out one of our molarities. So what we'll end up with is 1 over seconds molar squared. That's the same thing as seconds to the -1, molarity to the -2. So that's the units of our rate constant. Now, how would we actually find the value of our rate constant? Well, we would just have to use, find one entry in your table. So for example, for the first entry, all we'd have to do is plug and chug. So what you would do, in our first entry, our rate was equal to 1, the concentration of A is equal to 1, the concentration of B is equal to 1. We're not going to find anything too fancy. So 1 divided by 1 times 1 squared, which equals 1. So we're just going to end up with 1 reciprocal seconds molarity to the -2 for our units and our value of K. So I hope I've been thorough in explaining how to solve for rate laws, what rate laws are, and how you can use algebra to figure them out. If you have any questions, please leave them below. If you have any suggestions for any other videos or what other subjects you'd like to see, please leave them below or send me an email. Thank you very much and have a great day.